Okay, good morning. We will start the SolidWorks session. So today I'm going to look at the rest of the mechanical mates. We will start with, I think I ask you to download these toolboxes in your computer. So I'm going to start with these rack and pinions and gears and universal joint also I will show you. So if you don't have the files, you need to install the libraries in your computer. So design library should be available. So I will start the session. So I will share some of the files with you uh, now with an email. So I'm going to share this rack. I hope everyone is having this rack and pinion folder with you. Then I will share the universal joint file. So this will be shared with you. So if you don't have this, please, I will email now. Then Pinion, universal joint, and the gears. So I will email this now. If you don't have the files with you, I will send to Himanta also. So have this file in your computer. This is about the universal joint. So I will explain. I downloaded this from the internet, so I will show you how the universal joint works in SolidWorks. Uh, Before that, we will look at rack and pinion and the gears. Then our mechanical mates are over. So email I'm going to send now. So hope you have the rack and pinion with you. So you need to have rack and pinion also with you to today's lecture. So download this file and we will use this in a while. So I hope everyone is having this gear, this design library in your machine. So if you don't have this, you need to install the design libraries. These one toolboxes, design libraries. So I hope you have it. So when you have it, you can just go to this toolbox. Uh, so if you don't have this one at the moment, you have to install this. Software will automatically do that installation with you. So if you have installed it, you need to just take any standard. Say I take anti-metric. Then when you go down here, you find power transmission and bearings, bolt and screws. Everything is available. So I don't need to draw these things. That's the whole idea of using this design library. So last year exam also we ask you to use these design libraries. You can draw your gears or you can use the libraries and complete your work. So I can go to power transmissions here, you can go to gears. You will find a set of gears here. So we have the
Excuse me,
yes.
sir, when we click the toolbox thing, we get toolbox is currently running while that is actually a single user environment. They ask for ANSI, INSH, NC standard metric? What should we select?
Normally, I selected NC metric in my one.
Uh-huh.
I select
Okay.
metric. It's about millimeter. This is American National Standard Institute. And see,
Okay.
normally we will have metric. So
Okay. Okay. Okay, sir.
if you haven't installed this one, you need to do that. So you can just uh, follow the process they ask, or else you can just look at the YouTube and install these libraries. Uh, Now, if you have the libraries, we will use the Spurgear and I will show you how to use this. Now, last time when I used the Spurgears, we had a problem. Uh, there were some interferences with the gears. So when we made the gears, there were interferences. The animation worked, but there were some problems. So the problem is mainly due to the design issues. So when you do the gear designs, you have to actually use correct calculations and do that. So if you try to use this gear available in the
Hello.
list, yes,
Oh, Siva. Another. Open me. I don't make Niranga again. Manufacturing Tiba. The or Niranga Solidworks.
please mute your mics.
Boy,
Uh,
Sana in Nane.
excuse me.
Kaudabang Hanegan.
So, Chen, please mute your mic. Uh, Now, what I where was I? So I have to use this spur gears available in the libraries. So last week we had the issue. Uh, there were interferences with the animation. So I'm going to use this now. I'm in the assembly mode. You can just drag and drop this. So when you drag and drop this, it will give you some properties here. So in your design classes, mechanics of machine classes, you may have learned these things. What is meant by module, what is number of teeth, the angle, phase width. So these kind of information is important. So you can increase the number of teeth, you can change the module. So when you change the module and the number of teeth, your diameter will be changing. So this is important in SolidWorks. Pressure angle also important, and phase width is the width of the gear here. So when I increase this to say 5, enter, it will increase the size. So you can have a small width, something like 1. And module and the number of teeth are important here. So there's an equation related to module and number of teeth. So if I just Google it and find it out, you may have learned this in the design classes. So there's an equation like this. Module is equal to diameter divided by the number of teeth. So now the reference diameter of the gear. This diameter is important when you try to mate two gears. You have to decide the distance between the gears. So this diameter is important. So in my application, my module is 0.25, number of teeth here are 10. 0.25 times 10 is 2.5 millimeters. So in my calculation, I have to multiply this by this and I will get 2.5 as the diameter of the gear. So this is important when you try to assemble. So remember these two values 0.25 and 10. So I'm going to multiply 0.25 by 10 and get the diameter. This is the diameter. Actually, this is the PSD, pitch circle diameter, PCD. So this is important. So remember that one. Now I imported the gear. We can import another one if you want, same sizes. Let's escape. Now two gears were important. So you can see one is fixed now. So you have to make it float. Now I have to have a gear which can be rotated freely. So we are going to do that now. We are going to use some planes and try to create axes. So this thing I hope you can remember. Now I have created an axis. This axis should be mated with another temporary axis. So I can make this axis with the center axis. So I use the axis I created here as well as I use the temporary axis of the gear. Okay. Now this can be freely rotated, but it's going here and there. So to avoid that one, so if I just try to rotate it, this is machine is slow. This is rotating, but it's going here and there. So we have to avoid that motion. So you can use the plane, say the standard planes and this kind of a face easily and use a mate. Now it's almost okay. Now we are getting a gear which is freely rotated. So I hope you are. We have done this several times, several weeks. We have done this rotating gear mechanisms. Now this should be also uh, done like that. So I have to create another parallel plane. Now the distance is important here. Distance will be this. Distance will be 2.5. So I have to give this value 2.5. We can flip it. Now 2.5 is important. So 2.5 came from the calculation. So the 2.5 came from this calculation. 2.5 is equal to module is 0.25. This is 10. 0.25 times 10 is 2.5. Now we do the same operations again. Axis created. Then this axis is going to be mated with the center axis of the beam. Then this plane is parallel to this. So I'm getting two gears now. Okay. So you see, you can see there's a small diameter. This PCD diameter is also there. So I have got the two gears this way. So what can we do now? So have something like this in your machine. So I just drag and drop the spur gear, and when I drag and drop the spur gear, these properties, the properties appeared. So this multiplied by this one is 2.5. So from here to here, it's 2.5. So that value is important. And face width also I changed. So those are the things I did. So if you want to edit these properties again, you can go to edit toolbox components. You will get the same property palette again. So this thing can be again changed. Now if you get this basic promotion, now I'll use a gear mode. So we have mechanical makes, gears. You need to just select this inside circuits. So automatically this will be calculated. I can just press OK. Now if you have done this correctly, you should not get any interferences. You can see nicely it's animated. So last week we had issues. Last week we had some interferences. Now this week we omit that using the correct gear. So this is important. You can try this and see. If you have any questions, I will redo this. I hope you can remember the last week issue. Last week issue was the interference. So we managed to get rid of that problem. Important thing here is this module and the number of teeth property. So this is important. So here I have to use the equation, this equation. Then diameter is calculated. So the diameter is from here to here, but when you couple two gears, it's radius. So half of the diameter, half of the diameter. So it's 2.5 from here to here. So that's the value we need to use. Last time we didn't do that way. We just calculated the normal diameter and did that. That's the problem we had last time.
Can you again do the drag and drop thing? How to get this shape?
Excuse me. Can you tell again?
The gear. How to drag and drop and select the plane with the axis.
Okay, I repeat this again. So I hope you have the library. So we have to go to toolboxes. If the libraries are not there, you have to install that. Go to, I use the ANSI metric. Anything you can use. This is easy. Then I went to power transmissions. Then the gears. So we need to open assembly file. Otherwise, if you want to pass a part file, just drag and drop. So I need this as an assembly file. So I drag and drop this per view. So when I drag and drop this property palette will appear. So we need to remember these values. So you can change the module or the number of teeth, then the diameter will automatically change. And the face width is the width of the gear here. Pressure angle I didn't change. I didn't change the others. So that's okay. Now we can get another gear if I want and press the escape key. So now we have to do we have to animate the rotating gear. So how can I do that? Now first we need to create an axis. So this theory I have told several times. Remember this may be the easiest way of creating a rotating gear or rotating wheel. So this axis was created and I went to this temporary axis tool and enable the temporary axis tool. Then we went to make here. I took the axis I created here and the center axis of this gear. So it's giving an error because this is fixed. So I have to first make it float. Then do it again, this axis and the center axis. Done. Now once you do this, you are getting the rotating gear, but it's going here and there, back and forward. So to avoid that, we can easily use a plane like this. It's kind of a plane, original planes, and this view face. Now when I try to rotate it, it's nicely rotated. Same thing can be done for this other gear, but before doing that, we have to create another parallel plane to the front in my one. So that distance is 2.5. It can be this side or that side created, and that same procedures again. That plane coupled with another plane, you have to create the axis again, and that axis coupled with the center axis of the mate. Then this face and this. This is my way of doing this. This is not the only way of getting a rotated shaft or rotated wheel. So you may have different methods. This is my view. So it's not. It's actually fast compared to the other methods. Now we got the two gears freely rotating, and we have a tolerance here, the oil layer. So don't worry about that. Then we have to do the gear mate. Simple, that is simple. Just select this circle edge and this circle edge. Automatically the calculations have been done, and you need to just animate it and see. You can see how it works. So last year we gave this kind of exam question. We asked you to design a robotic gripper using the gears. So we can apply a motor now. It can be a rotary motor. I'll apply it. We can change the values and just animate it and see whether it's good. I have uploaded the videos to our YouTube channel also. So yeah, I had some suggestions to upload the videos to YouTube. So I have created a playlist also. So last 4 weeks lectures I have uploaded it already. So I have created the playlist also. So you find the SolidWorks sessions here, and previous AutoCAD sessions also available. So even Revit is available. So if you want, you can look at Revit also. So SolidWorks sessions, the last 4 weeks lectures are available in YouTube as you requested. Good morning everyone. So previous semester videos also available. So if you can forget anything, just go through these things and recap what I've done. So all the lectures in the semester 1 and semester 2 are uploaded to YouTube. Any questions about this? Any questions about this? We have to discuss universal joint and the rack and pinion. So rack and pinion also I will use our own files and show you first how it works. So I will close this now. So for the rack and pinion we have our part files. So we may have this folder and we need actually this also I downloaded from the internet the part files. So I'm going to use these two files and show you how to use the rack and pinion method. So we need to get the rack into our design. And the pinion also I can get it. It can be a spur gear. So these things I want in my design. So this should be floated and this should slide along a plane. So to get that sliding motion, what is the easiest way of getting the sliding motion? So I can use something like this kind of original plane and the face here and use a normal confident mate. Then we can, now this is coming here and there, but here and there. To avoid that, I can just use another plane like this and get a sliding back. Now this is sliding. So I use this kind of a coincident mate and another coincident mate like this. So these two mates will helps you to get a sliding back like this. Okay. Now this rack should be coupled with this pinion. So I have to have a freely rotating pinion. So we can now this is oriented in 90 degrees. So I just rotate it and get the correct orientations. This is enough. Then we have to create an axis. Axis also you don't need a so you can create an axis and do this, or else you can just without an axis also we can do this. So I will do it without an axis created. So what can we do? We do a normal mate like this. This face. Don't click on this face. If you click on this face, this will be acted as the parent. So don't click on this one. Click on the original planes. Now, this is the situation. So I use the original planes, not the planes. So when you select the planes here and mated with this one, when you slide this will also move. So that should not happen. So get the original planes because original planes are immovable. It's stationary. Those are stationary. Get it? Okay. Now we can do this kind of a thing. Manually we can take it down like this. If you want, you can get a calculation up to here and create an axis also. So that is not really needed. If you want, you can create an axis here. Now, I have done according to my eyesight. It may be enough. So I will go here and apply the rack and pinion method. For the rack, select the bottom edge, this edge, not the face edge. Then for the pinion gears, actually you can select the pitch circle diameter here, which we don't see, but here we can select this one, or else this one, or else these edges. So I will just select this one. Here there's a problem with this model because this was not done according to calculations. So you may not get that exact animation. So now when I rotate it, sorry, when I take the rack here, you can see it's happening. But here there's a interference issue. You can see there's an interference, but the animation works. Now when I try to rotate by the gear, it's not moving correctly because the gear is not fixed to the axis. This is happening this way. So if you want to do it very accurately, you have to create an axis. So I will do that now. Create a plane. So if you double click and check these values, this is 45, and this is 110. So the half of that one is 55. 55 plus 45 is 100. But you have to deduct this length. This length is 11.25. So around we have around 89, 88 distance from here to the axis here. So I hope you understood. This is 110. From here to here it's 55. From here to here it's 45. So 55 plus 45 is 100. But the gear should come inside a little bit. So 100 minus this value is important. Say around 89, 88 can be given. But since these are done roughly, you will not get the correct animation. Now I will create a plane which is parallel to this plane. I give a value, say 88, and this plane can be coupled with another plane, and we can create an axis. This axis should be coupled with the axis C. So this axis should be coupled with the axis in the B. Now you can see it's working, but it's not working in the correct manner. So if you try to rotate it like this, it's working, but there is an interference. So this is a problem we are having in rack and pinion. So because we are using someone else's files, so you can see there's a problem. You try this and see whether it's coming for you. And I'll show you a small video clip about the rack and pinion. So here they are doing the animation. Here they are selecting this as the reference. So you can see how they are selecting the mate references. So the first one, so they have selected this PCD as the pinion pitch diameter as the reference. So they have selected this this one. So I selected here. So that's the problem I am getting. You have to anyway select the bottom edge, and make sure you select this PCD here. So I don't have this design file. So when you do a rack and pinion animation, please select this as the PCD. Then you will get your animation working perfectly. So I hope you follow me. So I will show you how they are selecting this. So they selected this edge here, then this PCD. So these two are the important things. So then it will be okay. And he's trying to animate this. Now you can see it's working. So this is the target I need, but from the files I have, I can't get it. So if we give an exam question from this area, we may give the correct design. So don't worry about the exam questions. I hope you understood what I'm trying to say. So in my design, I can't see this PCD here. That's why I selected this edge. The theory is almost same. So this bottom edge should be selected definitely, and the edge I selected this one. In the video, they selected the PCD. So are you okay with this? So try to get a sliding back like this and a rotating wheel. And you need to just make these two from the edge of the rack. And I did it from this edge, but actually you have to do it from the PC. Here I can't find that PC in this design. That's why I use this edge. These are this also from the library. So you can see it's also from toolbox. This is also from toolbox. You have the module, pressure angle, phase width, pitch height, those kind of things are available. So you can get the same design from the toolbox also. Go to gears here, use this rack and this rack here. So if you just try to use this rack, this is the rack I'm getting. So you see a very small teeth because the height is very big. So I can just reduce the pitch height, say around 5, and this will be reduced. So this way I can change the track sizes. Face width also I can change. And the module also I can change. So these kind of things are available in the library also. So you can use the library to use this tool and the spurious and do the same design. Okay, is it hard to follow? I don't have any feedback. So shall I move to the next one?
Sir, hello.
Hello? Yes.
Sir, when we select the at the two gears at the point of two gears, we just we just slightly align those two together and just give the gear mate, right, sir? Is
Rack
it
and
like
pinion.
that?
In this rack
Yeah,
and
rack
pinion.
and pinion, yes, sir.
Yeah, you need to just orient it, say, just orient it like this a little bit.
Uh-huh. Uh, uh, like otherwise, the overlapping surfaces, they got overlap in here also, no, sir?
That is the problem.
We can remove it, right, sir?
We can remove it if you do a select. I selected this edge, but if you
Yes, sir.
select this PCD here as the video, so this video,
Yes, yes,
they
yes,
select
sir.
this.
So how can we have that? How can we have that diameter, sir? In our diagram, we had to draw it
Yeah,
separately.
when you do the gear teeth drawing, you have to draw this as a sketch.
Uh-huh.
Uh,
Okay, okay, sir.
the sketch using center line option, you can do.
Uh-huh. Okay, okay, sir. Okay.
I can't get it in my library file. That's the problem. So I'm using someone else's files. So this line is not visible in my part. That's the problem. So I try to go to the say since these are someone else's parts, we can't go and edit this. Say if I try to edit the part, it says you can't do that. Say I'll show you. Now these things are I think right protected. Uh, so because I haven't done this design, it's very difficult to edit someone else's designs. That's the problem. But if you do your own design, just make sure this uh, line is drawn PCD. So I think in your design classes they will teach you how to draw the tooth correctly. So this is a not a difficult thing. You just draw the shape and get a pattern. Uh, so if you do it according to calculation, this line will be there.
Okay, sir. Okay. Thank you, sir.
That's the problem we are having. So if you can give me a good file, we can show it in the class. So if someone can come up with a good design, we will show it in the class. Otherwise, the animation is working, but problem is it's not the real thing we want. Uh, it's not the real thing. Uh, Now we look at the last one, that is universal joint. So all these things are not available in my slides. So if you just look at our slides, we have the cabinet, pyramid, rack and pinion. We don't have files, so I found it from the internet. Screws, hinge also we have to find it. And I think Mr. Sean has done the tutorial, first tutorial, last few days ago. So he may have done that this tutorial with you. So we have some more concepts to discuss. Probably by next week we can finish our assembly theory. So we have some more concepts to discuss. We will discuss these things next week. Uh, Before we start these things, we will look at the universal joint. So that will be our last mechanical mate. So this also taken from the internet, this file. So this is a completed assembly. I don't need all these parts to show you the theory, but if I just open the full one, this is the full part, universal joint, full assembly. So anyway, why we need the universal joints before we start the theory? Universal joints will help us to do whatever the things we cannot do from gears. Normally gears we cannot have this kind of angle orientations. We have to have 90 degrees or say parallel. So universal joints will help us to get something transfer the motions at an angle. So in this animation, when you rotate this handle, you can see this part is nicely rotating. So this is the universal joint. And if you look at our the mates they have done, they haven't used the universal joint mate. That's interesting. So they haven't used the universal joint mates. They have used a lot of other concentric kind of mates, lot of other things, and they try to get that same function. So it's actually time consuming. Those days, I think they didn't get universal joints in the SolidWorks, so probably that may be the reason they haven't used the universal joint mate. They have used the traditional mates and have done this design. So if you just look at this area, tangent, concentric, and the width here, so these are more or less universal joint mates. So here we can't find any word called universal joint. So I have done a simplified design. I have given you the file. I think I shared with you through the emails. So we have a simplified file here. Simplified file doesn't have any handles, nothing, no pins, nothing. So in virtual world we can animate, no problem. So this is the universal joint. So here we don't find any pins, no rods, nothing, no sharps. It's working in the virtual one. So how can I get something like this? That's the question. So if I just look at the mate I did, it's, uh, it's the universal joint mate. So we can do it very quickly. Otherwise, if I use traditional things, you have to do a lot of other works. That's what they have done in the file I imported from the internet. So how can I do this kind of thing? That's our question. So if you delete this universal joint or suppress this universal joint, uh, this is just a normal rotation. This is just a normal rotation. This is another normal rotation. So I have done some concentric mates, some coincide here, another coincide here, another coincide, axis coincide. So these kind of things I have done. So I will quickly do it again and show you how to apply the universal joint in the SolidWorks environment. You will get the files. I shared the files with you a few minutes ago. We have this folder, and I'll take the bracket that should be there. It's the fixed part, and we need to have this yoke female as well as yoke male. So these two parts should be there. Now I need to have a freely rotating yoke male. So I will do some traditional mates. So this is now freely rotating. Then this one. So this one also we have to do it. And in this part, there is no hole here. So you need to align this center in the correct center here. But it's going to be difficult in this design because I don't find any centers. So I will just do this kind of a thing, and I have to put it in the exact center. So center is not available here. If you have a hole, you can easily use the concentric mates and align it. Here I don't have a hole here, so we can do what? There are a lot of ways we can easily create an axis and do that without drilling hole. So I will try to create an axis from the axis tools. So from the axis tools, if I try to do it, I need a point. So I have to have a point in the middle. So we will recall our previous semester knowledge and create a point in the center of face. So I created the point in the center of the face. This one, center of face. Why I'm doing this? I have to have an axis in the middle. So you can use this point and face plane. Consider this plane, face, and get an axis. So why I did this? Basically, I need to align the two axes in the middle. So we can use the mate here. There are a lot of other ways. This is one of the ways. And get this like this. So I got concentric coincident mates and coincident here. And I have the two parts in my hands. So this is freely rotating. This is also freely rotating. So try to have something like this in your computer. So have a freely rotated male part and a female part. So I hope you got the files. Now, now we will apply the universal joint. So it's not difficult. So before we apply the universal joint, please orient the parts correctly. So this part should be oriented this way, and this part should be oriented 90 degrees to this part. So how can I do it easily? To orient the parts, we have done a theory called positioning on limits. So we can use uh, the planes. So I will use this plane, and this plane should be parallel to this plane. So we can use a method called, there's a tool called in the bottom used for positioning only. So I'm going to use that one used for positioning only. We can use this space in this kind of things. So it should be perpendicular. So it's only for the positioning. Then this one also can be done that way. This part only for position. So I'm positioning the parts correctly, otherwise there will be interferences. Okay. So that's all you have to do. Then we will apply this universal joint method. So here we have to just select the two yolks. When you select the two yolks, it should work. If you have problems with interferences and other things, you have to define the joint point. So joint point is the point going through the center axis here and the center axis here. So there is an axis going through this one. There's another axis going through here. So those two axes will meet at a certain point. So you can create that point and select that point as the joint point. So yeah, I don't need that in my case. If you have problems with interferences, just try to apply that joint point. So you can use the axis here, another axis here, and those two axes will meet in a certain point. Create that point and define it. So if you try to define it, there will be a middle point in the drawing. So I don't want this. Now, since these are someone else's files, we don't know whether there are interferences or not. But you can see how it works now. So this is the universal joint mechanism in SolidWorks. So you can see some interferences happening. So to avoid those things, we have to define the point, or else we have to do the correct designs. Just do this thing and see whether it's okay for you. Design I'm going to show you now. I said that there are interferences happening. So if you want, you can use the software tools and try to detect it. So there's a tool called interference in an assembly, checking the interference. So it's very easy. You can just go to evaluate and use this interference detection tool. And there's a button called calculate. It will automatically show you the interferences you are getting. So if you want, you can ignore that. So else you can come here and exclude some parts. So those options are available. So just use this tool, and before doing the manufacturing, better you run this test and see. So these values will be shown. And another file is available in our part file list 1311. So we can detect the collisions even. So the interferences, collisions, all can be detected. So it's available in my slides. Analyzing collision detections. So you can animate this and see. So you have to use on the evaluate. You don't find the collision detection. You have interference detection. So under assemblies, under moves, move components, we have this collision detection mode. So what you can do is you can just animate it and see. Now you can see it's colliding. You get a sound. So and if you want, you can stop at the collision. So you know. So these kind of things may be important in your animations or before the manufacturing. Just check these things and send the part to the manufacturer. Okay, so these is not available directly. So interference detection is available, but here if I calculate it, no interferences. So interference detection, we have to manually take this here and get this value. Otherwise, it won't detect. But the collision detection is much more advanced than that. So you can go to assemblies, get the new components, collision detection, and stop at collision, get a sound, highlight the phases, and make something like this. Okay, I hope you are following my here. So evaluate, you have the interference detection as well as in the assembly and the new components, you have collision detection. Now we look at how to apply this tool, hole alignment tool. So if you have holes assembled together, so if you want to detect these misalignments, we can ask the software to do that. So how can I do it? So I will use the file available here. So we have two plates. We'll assemble this quickly. I'm going to use some traditional methods and assembly. I have done an assembly. You can see clearly there's a misalignment. So I didn't use the circles and I didn't use the concentric lines. I just used the normal flat planes and I did an assembly. So when you look at it as a wireframe or hidden lines, you may see a misalignment here. There's a small misalignment. So we can ask the software to detect that. So there's a tool on the evaluate all the alignments. Uh, this is the tolerance I am going to expect. So under 10 millimeters, it will not detect. So if you calculate, says sorry, more than 10 millimeters, it will not detect. It says maximum deviation is 1.4. So it will show you the parts which have the problem. But if you say 1 millimeter here, it will not detect. No misalignment. So below 1 millimeter, there is nothing. So it will say 2, it will detect 1.4. So you can have the maximum value you want to have, and quickly you can calculate it and get an idea where are the misalignments. So this is also really important tool when it comes to manufacturing. So you can assemble this in a traditional method and go to evaluate and hold alignments. Just give the tolerance, maximum tolerance you expect in 5 millimeters, and it will detect less than 5 times. If you say 1 here, it will not detect because the deviation is more than 1.5 even. Okay, so you can try this at home. I'll finish the class for today. Next week we will look at how to create the sub-assemblies, how to use the top-down approach. So this approach is important. How to use the top-down approach, how to replace the mates, how to dissolve the sub-assemblies, how to replace the components, those kind of other areas. feature-driven mirror components, copy tools, interference I did, all alignments I did, connection detection also I did, and we have to do the exploded bits. And that's all for the assembly. So probably next week we can finish this. So I will stop for today. So if you have any questions, you can always contact me. I will upload this video to YouTube and Scope. Thank you for participating.